Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIWA campus. In this video, we will cover the contents Fourier and inverse Fourier transform examples, and we will discuss Fourier transform properties as well. Let's take another example about the calculating the Fourier transform of a signal. For example, you have to find the Fourier transform of the following rectangular pulse signal. What is rectangular pulse? For example, it looks like in this way. It has a value greater than, it is value equal to 1 for t less than t1 positive side and minus, and on other side it is 0, right? So this is rectangular pulse. And so using the equation to find the Fourier transform, you know that x j omega equals to minus infinity to infinity x of t and e minus j omega t dt. Now putting the values of x of t, you know that x of t is equal to 1 for the given range minus t1 to plus t1, right? So replace infinity with minus t1, with minus infinity with minus t1 and positive infinity with positive t1, and x of t is equal to 1 into e minus j omega t dt. And after integration, because it is a time integration, so you will get minus e minus j omega uh, in the integral, and after putting these limits you can get e minus j omega t1 minus e minus j omega minus t1, which become e j omega t1 plus uh, e minus j omega t after rearranging. So multiply and dividing by 2, we can write the in terms of sine as well. So after some manipulation you get 2 sine omega t1 over omega. So this is your Fourier transform, right? So this is nothing much special. So just have to evaluate the integral, and using the some trigonometric expressions you can get this term easily. So you can verify yourself as well. So this is the description of the example which we just discussed. For example, reducing the width of the xt. This is your original signal x of t, which is a rectangular pulse. If you reduce the width means this t1 duration. If you reduce this time duration, then it will have an opposite effect on xj omega t. This is opposite effect means that you are doing a reduction in time here, so it is expanding in frequency here. So using inverse Fourier transform, if you take the inverse, this is the Fourier transform of x of t. If you take inverse of xj omega, then you can get x of t. What he said here, it means that using the inverse Fourier transform, we can get the x rectangle. This is rectangular function which is equal to x of t, so which will be equal to x of t like this one, whereas except at discontinuities, this is discontinuities because there are sharp transition t1 and minus t1, where the inverse Fourier transform is equal to the average of the values of x of t on both sides of discontinuity. As I discussed in the previous class or previous video, that these fluctuations, if you can see these number of fluctuations here and on this side as well, it will continue till infinity, right? Or infinity means for the larger number of frequencies. So to get this sharp point, you have to take average on this side and this side. After getting this, combining all this, then this can be equivalent to this sharp transition. Let's take another example to find the inverse Fourier transform. For example, find a time signal. Inverse Fourier transform means you have to convert frequency domain into time domain. So for example, you have a time domain signal given, you have to find a time domain signal which is x of t and whose Fourier transform. Now we have given the Fourier transform x j omega is equal to 1 for omega less than w and omega greater than w is 0. Its shape will be similar because it is a rectangular function, but the axis will be different because now we have a w here or omega here, right? Omega is w equivalent to w and minus w, and the amplitude is 1 here, and for the rest of position it is 0. So now to find the inverse Fourier transform, x of t equals to 1 over 2 pi x j omega e j omega t d omega. So by putting the values of x j omega, which is 1 for w to minus w to w, just putting that limit and putting 1 instead of x j omega and e j omega t d omega. So after taking the integral, you can get e j omega t over 1 over j omega, right? And 2 pi is already there. So 1 over 2 pi j omega, and the limit will be from minus w to plus w. And now instead of this omega, you will put the w, and after solving, you can easily get this sine w by wt over pi t. So sine wt by pi t by just doing some algebraic manipulation. It is very easy, so you can try yourself as well. Because using the 1 over 2j e j theta plus e minus j theta, you know that it's equivalent to sine theta. So using the same identity, you can get this output as well, right? So this example shows the reverse effect in the time and frequency domains in terms of the width of the time and the corresponding Fourier transform. So here you have x of j omega, which I already plotted. This is your the Fourier domain signal or the frequency domain signal because omega is axis here. And if you take the inverse, you will get this type of a function. This is sine w t over pi. So this will continue and for infinite number of time, and here the axis is time instead of frequency. Another important functions are the sinc functions. Usually there are two types of sinc function. One is called normalized and other is called non-normalized functions. And usually in digital signal processing or signal and systems, we use the normalized sinc functions. So what is sinc function? First we have to know, check that one, right? Sinc function, as I already plotted in the previous slide, you saw the function that continues for a long time in this way, right? Its side lobes continues for the right. This is kind of a sinc function, right? Sinc, S-I-N-C, sinc. So in general, sinc theta, if you write sinc theta, S-I-N-C theta, which is equivalent to when it is normalized, right? Normalized, it is sine pi theta over pi theta. These two angles should be same. The angle should be in the denominator as well. So this is called normalized. Why normalized? When there is a pi here, then it is called normalized. And when it is non-normalized, it will be written in this way. In mathematics, usually they write sine t equals to sinc t equals to sine t over t. Right? So this will be a non-normalized case. What is the difference between normalized and non-normalized? In normalized case, the zero crossing this point, for example, this point where the graph cut at 0, x-axis is cut by the graph at the x-axis is the signal is 0 at x-axis, right? So this is called the zero crossing type of signal. So at this point, for the normalized, this is normalized, you will get the integers multiples, for example 1, 2, 3, so on. Whereas for the non-normalized case, you will get some pi terms here, right? So this will be a major difference. So we will focus on the normalized case like this type of function, saying theta is equal to sine pi theta over pi theta. It is equivalent to this function. So in the previous example, we have seen that we have a sinc omega t 1 over pi So we can write, we can think that omega t1 over pi is theta here, right? If we replace by theta, so just put the value of theta here. For example, sine pi into omega t1 by pi over omega t1 by pi into pi. So this pi will be cancelled out. So it means that sine omega t1 over pi equals to sine omega t1 over t1. So we can write sine omega t1 over t1 equals to, using sinc function, you can write equals to sine omega t1 over pi equals to sine omega t1 over omega t1. So you have given this one already. You have noticed that by taking the solution, you have when you solve the inverse Fourier transform, you get the sine omega t1 over omega. So just multiply by t1 and divide by t1, so it becomes equivalent to this one, right? So you can replace with sine omega sinc omega t1 by pi. So it is equivalent to 2t1 sinc omega t1 over pi. Similarly is the case for the other signal. There is another signal as well which is equal to sine omega t over pi t, and by just doing values, putting values and cutting, you will get sine omega t equals to sinc omega t by pi. So this is a sinc functions. So these sinc functions are usually used in communication in number of ways. So functions of the form sine ax over bx are very frequently used in signals and systems. In general, the function sine pi x over pi is referred to as a sinc function, as I already mentioned. Pi theta or pi x, same meaning. So the time signal of example, we can express sinc function as follows: sine omega t by pi t, I already derived in the previous slide. So equivalent to w by pi sinc wt by pi. So this is, so you can write this in terms of sinc function basically just by doing some manipulations. Okay, now discuss the properties of continuous time Fourier transform. Why we need properties? So the properties has the advantage. The properties are useful in determining the Fourier transform or inverse Fourier transform. Why and how? They help to represent a given signal in terms of operations, example convolution, differentiation, shift, on any other signal for which the Fourier transform is known. For example, if you have a known Fourier transform of some signal, and you can just, for example, you want to multiply two signals, and in time domain it will be multiplication, but when you convolve, it will, whereas in frequency domain it will be convolution. So using different properties, you can easily solve the complex signals as well. So operation on xt is equal to operations on x j omega. So if you have some operations on xt in time domain, so in Fourier domain you have some operation on omega domain, which is x j omega. So it helped in finding analytical solutions to Fourier transform problems of complex signals. For example, you need to find a Fourier transform y of t equals to a t u t minus 5. So there are two types. One is delay here and the other is multiplication. So you can just separate them and multiply them and then take the Fourier transform. So it will make the process some easy process, right? It will reduce the complexity as well. So these are some properties you will now we will study here, and further on you can use to solve the complex problem by breaking into two problems, three problems, and applying different properties. You can solve that problem easily. So the properties of the continuous time Fourier transform are very similar to those of the continuous time Fourier series. For example, consider two signals xt, yt with Fourier transform xj omega, yj omega respectively. Or in for if this is omega domain, if you can write that in frequency domain as well. So omega and frequency is same, like you know that omega is equal to 2 pi f. So there is only difference of 2 pi between omega and frequency. So there is nothing much difference, just the scaling factor of 2 pi will be difference, right? So usually they write x j omega, or sometimes they also write x of f. So they both are same. Like this is the Fourier transform x j omega in omega domain, and x of f is also the Fourier transform of a signal but in frequency domain, right? The following property can be easily shown using For example, x j omega is equal to minus infinity to infinity xt e minus j omega t dt. This is our Fourier transform calculation formula. Okay, let's discuss the first property, which is linearity. We already discussed in the Fourier series linearity property. Here we are discussing again in terms of a Fourier transform. So for example, you have x of t, you take the Fourier transform which is equivalent to x j omega. You have another signal y of t, you take the Fourier transform, you will get y j of omega. And linearity, it means that you multiply by some linear constant, for example alpha, with x of t, and then add them. So and multiply the other signal with beta and then add them in time domain. It is equivalent to multiplying the alpha in frequency domain and adding them and alpha in frequency domain with the Fourier transform of x of t, and the addition plus beta into y alpha. So you can write in this way. Or similarly, if you want to write in j omega domain, so it will be equivalent to this one. So this is linearity, and this is the mathematical representation. For example, x of t into alpha, y of t into beta, block diagram representation, not mathematical, plus into, then take the Fourier transform, because this was in time domain, this represent Fourier transform. So alpha x of f plus beta y of f, right? The other property is time shifting. What does it mean? For example, if you have a given signal in time domain x of t, and when you take the Fourier transform, it is equivalent to x j omega. All of you know that, right? So when you shift in time, for example, time is shifted or delayed or advanced, for example, by t naught, right? T minus t naught. It, instead of t, it becomes t naught. So we want to see that what will be effect in the frequency domain. So you will get e minus j omega t naught x j omega. So let's prove first and then discuss what does this equation mean. So to establish this property, consider the inverse Fourier transform, which is equal to 1 over 2 pi minus infinity x j omega e j omega t d omega. So now replace t with minus t naught. So we replace t with t minus t naught, and here the t is also replaced by t minus t naught into d omega, and you can see that e j omega t into minus j omega t naught. So by combining them, e minus j omega t naught x j omega into e j omega t d omega. Recognizing this as a synthesis equation for xt minus t naught, we conclude that, so if you uh, separate them, for example, you know that this part is equal to, because this part is, and this part, right? If you combine these two, so this is nothing else just x of t, right? So this nothing just x of t, right? So recognizing this as a synthesis equation for xt, we conclude that Fourier transform of xt minus t naught equals to e minus, because this term is constant, as there is no e minus j omega t naught, because this is the function of d omega, not t naught. So we can take this outside. So it is equivalent to e minus j omega t naught into x of j omega. So from here we notice that one consequence of time shifting property is that the signal which is shifted in time does not have magnitude of its Fourier transform altered. So it means that when you shift the signal in time, the magnitude of the Fourier transforms and the magnitude of your signal Fourier transform is not changed. What happened? Only the change is in the time in the phase of the signal, which is e minus j omega t naught. When let's represent in the polar form, for example, x of j omega is complex term, so it has a angle, it has a magnitude and a phase. So putting these terms, instead of t, put t naught minus t naught, so you can write e minus j omega t naught x j omega. So x j omega is amplitude, phase is j omega minus omega t naught. So thus the effect of the time shift on a signal is to introduce into its transform a phase shift, namely minus omega t naught, which is a linear function of omega. So from what we conclude here, what we conclude from here, we concluded that transform in time shift will introduce a phase shift in the Fourier transform. So whenever there is a delay in time of a time signal in the time domain, so whenever you take the Fourier transform, there will be nothing change in the magnitude of a signal, whereas there will be a phase shift in the signal, resultant signal. There are some other properties. One is called time reversal. Time reversal means that if you have a x of t, you take the Fourier transform, you will get x j omega. However, what will happen if you time reverse the signal, original signal x of minus t? So then the Fourier transform of that signal will be the frequency domain. You have a magnitude which is also reversed as x minus j omega. So same effect. The other property is the time scaling. Time scaling means that if you have a signal x of t, instead of x of t, you have a x a of t. So whenever you take the Fourier transform, what will its effect? So there will be a division with the same scale link factor, and you can get x f over a. So there will be this is called a time scaling property. And this is x f over a. If you can want to write in omega, so it's same, but with some writing difference, little bit difference. X j omega a. The other term is frequency scaling. So whenever you scale the signal with a frequency, like 1 over a x t over a, so you will get in the Fourier domain, you will get a x a of f. So whenever you multiply the signal with some scaling factor, then in frequency domain you have a frequency scaling as well, and this is omega domain. So these two equations meaning is same, but writing is different. As I mentioned, there is some scaling factors issue because omega is equal to 2 pi f. The other property is the conjugation and the conjugate symmetry. Conjugation, does it mean, and the conjugate symmetry, let's discuss. For example, you have x of t is Fourier transform is x t omega. So you want to take the conjugate of a signal, for example x conjugate t, then what will be effect on the Fourier transform? So in the result you will get the conjugate x conjugate, and with the frequency reversal with the minus sign as well. For example, for real signals, we have x of t equals to x conjugate. In real, you know that conjugate is equal to the original signal. So which result in the following conjugate symmetry. What is that symmetry? For example, x minus j omega, because this is real. So in case of a real, x minus j omega is equal to x conjugate j omega. So they both are same. This implies that for a real signal, the real part and the magnitude of x j omega are even functions of w. So for real signals, the real part and the magnitude are even functions, while the imaginary part and the phase are odd functions. So what is the difference between even and odd? You know that for even, when there is a minus sign, when you multiply with minus sign, in the end you have a no impact on the real part as well. So its result is same, minus x, for example, real of x of j omega equals to real of x of minus j omega. There is nothing changed, right? So they both are. Whereas for imaginary, the odd function, because the imaginary part is odd function, you can see that imaginary x j omega is equal to minus of imaginary x minus j omega. So there will be additional minus sign here as well. For magnitude, x of j omega is equal to magnitude x of e minus j omega, whereas the phase x of j omega equals to minus x of minus j omega. So this is the property conjugate and conjugate symmetry, and you can see that how to find the Fourier transform of this signal as well. The other is multiplication and convolution. For example, you might have a signal which is convolved in time domain. This sign shows the convolution. You have two signal xt, yt, they are convolved in time domain. So what happened in the frequency domain? So when you take the Fourier transform, so you can simply multiply this instead of convolution, x of f by f. And similarly, in this was in f domain, if you want to write in omega domain, so x of t in convolve yt equals to x of j omega by j omega. And this is the multiplication convolution duality. Duality means that reverse is also true. Reverse means, for example, previously there was a multiplication sign here, convolution sign here. Now if you just multiply in time domain, it is equivalent to convolution in frequency domain. So x of f in convolved via. And for omega, you can have a 1 over 2 pi x g omega convolved via g omega. So the other property is differentiation and integration. So these property can be used whenever required. For example, you have a x of t time domain signal and you differentiate that one, right? So differentiation operation in frequency domain is just the multiplication of j omega with the magnitude, right? So it will make the differentiation easier in frequency domain. So whenever there is difficulty in solving differentiation, you can just convert the x of t into Fourier domain, Fourier transform, and then just multiply with the j omega. So it is the operation is similar to differentiation. And for integration, you have to take, for example, minus infinity infinity x of tau eta, and its operation is similar in frequency domain as 1 over j omega. So just by scaling some factor and into the x of j omega is the Fourier transform plus pi x of 0 means a 0th sample into impulse of w. So this is a general equation you have to remember. You can prove that as well, but it will definitely take some time. The other property is Parseval's equality. What does it mean? Parseval say that in time domain, if you want to find the energy of a signal, because this is energy x t square is energy. So you have to integrate within the given period of time. And similarly, if you want to find the energy of a signal in frequency domain, what you have to do? You have to integrate for all frequency components x of j omega at square minus 1 over 2 pi. So this energy in time domain will be equivalent to energy in frequency domain. So this is the summary of properties of continuous time Fourier transform, and there can be number of properties, and some of them are listed here, and they have their own advantage. Linearity we discussed, time scaling we already discussed, time shift, and differentiation, integration, and multiplication and convolution, multiplication, so on. So these are some properties we already discussed, and that's all.